Only 40 light-years away, there is a star system so peculiar that it could change everything we know about life beyond Earth. The TRAPPIST-1 system, first discovered in 1999, seemed insignificant at first. It took 17 years of advanced telescopic observation to uncover its secrets. 7 Earth-sized planets orbiting a red dwarf star. By 2017, astronomers realized they had stumbled upon a potential gold mine for the search for extraterrestrial life. Some of these rocky worlds might hold more water than all of Earth's oceans combined. But there's a catch. Studying these distant planets isn't easy. TRAPPIST-1's frequent stellar flares and the sheer distance pose significant challenges. Thanks to the groundbreaking James Webb Space Telescope, scientists can now delve deeper into these worlds. How habitable are these planets? And what would life be like on them? As you're peering through the sky with your telescope, you stumble upon a star system so extraordinary, it could redefine our understanding of the universe. That looked like the beginning of a science fiction movie, right? Well, in 1999, astronomers did just that when they discovered TRAPPIST-1, a faint red dwarf star located about 40 light-years from Earth. Initially, TRAPPIST-1 seemed like just another star among the billions in our galaxy. Little did anyone know, it was harboring a cosmic secret that would fascinate scientists and space enthusiasts alike. For years, TRAPPIST-1 remained largely unremarkable, a dim point of light in the vastness of space. But in 2016, everything changed. Using the TRAPPIST, Transiting Planets and Planetesimals Small Telescope in Chile, astronomers observed the star's light dimming at regular intervals, suggesting planets were passing in front of the star. Initially, 3 Earth-sized planets were detected, orbiting tantalizingly close to their parent star. The excitement didn't stop there. In 2017, the Spitzer Space Telescope revealed that the system wasn't just home to 3 planets. It had 7 rocky planets, all similar in size to Earth. This discovery was groundbreaking. Never before had scientists found so many Earth-sized planets in a single star system, especially ones so close to potentially habitable zones. The 7 planets of TRAPPIST-1 are named simply and systematically TRAPPIST-1b, C, D, E, F, G, and H. 3 of these planets, TRAPPIST-1d, E, and F, and potentially a 4th one, TRAPPIST-1g, reside in the habitable zone, the region around a star where conditions might be just right for liquid water to exist. This is crucial because water is a key ingredient for life as we know it. The prospect of finding water on one or more of these planets ignited a flurry of research and speculation about the potential for life beyond Earth. TRAPPIST-1's planets are remarkably similar in size and mass to Earth, but their star is very different from our Sun. TRAPPIST-1 is an ultra-cool dwarf star, much smaller and cooler than the Sun, meaning its habitable zone is much closer. The planets orbit very tightly around TRAPPIST-1, with the farthest one, TRAPPIST-1h, still closer to its star than Mercury is to the Sun. Despite their proximity, these planets could have conditions suitable for life due to the star's lower heat output. The discovery of the TRAPPIST-1 system has profound implications for our search for extraterrestrial life. It suggests that potentially habitable planets may be more common than previously thought, especially around red dwarf stars, which are the most common type of star in our galaxy. The TRAPPIST-1 system, with its 7 rocky planets and 3 in the habitable zone, offers a unique laboratory for studying the conditions that might support life. The James Webb Space Telescope, JWST, launched in 2021, has been a game-changer in this regard. Equipped with advanced instruments capable of analyzing the atmospheres of distant planets, JWST has been focusing on the TRAPPIST-1 system to look for signs of water, oxygen, and other biomarkers. These observations are crucial in determining whether any of TRAPPIST-1's planets could truly be habitable. If you're liking the video so far, you should consider subscribing to the channel and help us create better content and reach more explorers out there. Now back to the video. TRAPPIST-1b, the innermost planet, orbits closest to the star at a mere 1.5 million miles away. It's a scorching world with a surface temperature estimated to be around 450 degrees Fahrenheit or 230 degrees Celsius. Due to its proximity to the star, TRAPPIST-1b is likely tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. This planet is too hot for liquid water and is unlikely to support life as we know it. Next in line is TRAPPIST-1c, orbiting slightly farther out. This planet also experiences extreme heat, with surface temperatures around 225 degrees Fahrenheit or 107 degrees Celsius. Initially, scientists thought TRAPPIST-1c might have a thick atmosphere similar to Venus, but recent data suggests otherwise. TRAPPIST-1c likely has a thinner atmosphere, making it a rocky, barren world with harsh conditions, unsuitable for life. As we move outward, we reach TRAPPIST-1d, a planet that has captured the interest of scientists and space enthusiasts alike. TRAPPIST-1d is the lightest of the planets, with about 30% of Earth's mass. It's located on the inner edge of the habitable zone, where conditions might be right for liquid water. Without any atmospheric effects, the temperature on TRAPPIST-1d would be around 48 degrees Fahrenheit or 9 degrees Celsius. This planet is a prime candidate for further study, especially with its potential to harbor vast amounts of water, possibly up to 250 times more than Earth. TRAPPIST-1e, often considered the most promising candidate for habitability, is situated right in the middle of the habitable zone. This Earth-sized planet is dense and rocky, suggesting a solid surface where life could potentially thrive. TRAPPIST-1e receives similar amounts of solar radiation to Earth, which could mean surface temperatures conducive to liquid water. Its similarities to Earth make it a focal point for the search for extraterrestrial life. TRAPPIST-1f, located slightly farther out, also resides within the habitable zone. This planet might have conditions suitable for liquid water, depending on its atmospheric composition. If TRAPPIST-1f has a thick atmosphere, it could retain enough heat to support liquid water. Its larger size compared to Earth suggests it might have a substantial atmosphere, but this remains speculative until further observations are made. TRAPPIST-1g, near the outer edge of the habitable zone, is another intriguing world. Its size and mass suggest it could have a significant atmosphere, potentially allowing for liquid water to exist. However, its position means it receives less solar radiation, resulting in colder surface temperatures. If TRAPPIST-1g has a greenhouse effect similar to Earth, it could maintain liquid water on its surface. Finally, we reach TRAPPIST-1h, the outermost planet in the system. This planet orbits just beyond the habitable zone, making it a frigid world with surface temperatures likely too cold for liquid water. However, if TRAPPIST-1h has geothermal activity or a thick atmosphere, it might still possess subsurface liquid water or habitable conditions in certain areas. With its relatively small size and mass, TRAPPIST-1d stands out as a world that could potentially harbor life, depending on its atmospheric and surface conditions. TRAPPIST-1d is the lightest of the 7 planets in the system, with a mass approximately 30% that of Earth and a radius about 80% of Earth's. This small, rocky planet orbits its star at a distance of about 2.25 million miles, placing it on the inner edge of the habitable zone. In this position, TRAPPIST-1d receives a significant amount of solar radiation from its parent star, but not so much that it would be uninhabitable. The climate and atmosphere of TRAPPIST-1d are crucial to understanding its potential for supporting life. If TRAPPIST-1d has an atmosphere similar to Earth's, it could maintain surface temperatures that allow for liquid water. Estimates suggest that this planet could have up to 250 times more water than Earth. If TRAPPIST-1d is covered by a global ocean, it could create a stable environment conducive to life. Albedo, or the measure of how much sunlight a planet reflects, plays a critical role in determining its climate. Earth's average albedo is 0.3, meaning it reflects 30% of the sunlight that hits it. If TRAPPIST-1d has a similar albedo, it could reflect enough sunlight to avoid a runaway greenhouse effect, maintaining a more stable and habitable climate. TRAPPIST-1d's potential habitability also depends on its geothermal activity. A strong tidal heat flux, driven by gravitational interactions with nearby planets, could provide additional heat and energy. This is similar to the geothermal heat on Earth, which supports life in deep ocean vents. If TRAPPIST-1d has a tidal heat flux 20 times stronger than Earth's, It could drive chemical reactions in the planet's oceans, creating conditions favorable for life. On Earth, some organisms derive energy from chemosynthesis, a process that uses chemical reactions instead of sunlight to produce food. These organisms thrive in extreme environments, such as deep-sea hydrothermal vents, where sunlight never reaches. If TRAPPIST-1d has similar environments, it could support life forms that do not depend on sunlight. Another intriguing aspect of TRAPPIST-1d is its twilight zone, the boundary between its day and night sides. Because TRAPPIST-1d is likely tidally locked, with one side always facing the star and the other in perpetual darkness, the twilight zone could offer a habitable region with stable temperatures. In this area, the conditions might be just right for liquid water to exist, providing a potential refuge for life. Among the intriguing planets in the TRAPPIST-1 system, TRAPPIST-1e stands out as the most promising candidate for potential habitability. Imagine a planet that shares striking similarities with Earth, not just in size, but also in composition and potential for life. Located in the habitable zone of its parent star, TRAPPIST-1e could very well be the cosmic twin we've been searching for. TRAPPIST-1e is dense and rocky, with a composition that might mirror our own planet. This density suggests a solid surface where life could potentially take hold. What makes TRAPPIST-1e particularly intriguing is its position within the star's habitable zone, the region where conditions might be just right for liquid water to exist on the surface. Without atmospheric effects, TRAPPIST-1e's equilibrium temperature hovers around a comfortable 0 degrees Fahrenheit, or minus 17.5 degrees Celsius, similar to Earth's without its greenhouse gases. The planet's potential for habitability is further underscored by its similar size and mass to Earth. TRAPPIST-1e is about 91% the size of Earth, and has approximately 77% of Earth's mass. These characteristics suggest it could have a gravity and atmosphere similar to our own, which are crucial factors for maintaining liquid water and supporting life. The amount of solar radiation TRAPPIST-1e receives is comparable to what Earth gets from the Sun, providing the right energy balance for potential ecosystems. One of the most compelling aspects of the planet is its potential to support liquid water. Water is a key ingredient for life as we know it, and the conditions on TRAPPIST-1e might allow it to exist in liquid form. If TRAPPIST-1e has a substantial atmosphere, it could create a greenhouse effect, warming the planet enough to maintain liquid water on its surface. Interestingly, TRAPPIST-1e's atmosphere, if it exists, could offer clues about its geological activity. A planet with active geology is more likely to recycle nutrients and support a stable climate, both of which are important for sustaining life. Volcanic activity, for example, could release gases that form a protective atmosphere and create a greenhouse effect, warming the planet. Additionally, tectonic activity could foster diverse environments where life might thrive. Earth's magnetic field protects us from harmful solar radiation and helps retain our atmosphere. If TRAPPIST-1e has a similar magnetic field, it could shield the planet's surface and atmosphere from the intense radiation of its parent star, making it a more hospitable place for life. Despite its many promising features, TRAPPIST-1e's habitability is not guaranteed. The planet's proximity to its star means it is likely tidally locked, with one side perpetually facing the star and the other in constant darkness. This could result in extreme temperature differences between the two hemispheres. However, if TRAPPIST-1e has a thick atmosphere, it could help distribute heat around the planet, creating more temperate conditions. Our last contestant as possibly having conditions that support life is TRAPPIST-1f. TRAPPIST-1f orbits its star at a distance of about 5.5 million miles, placing it squarely in the habitable zone where temperatures could allow for liquid water to exist. The planet is similar in size and mass to Earth, with a radius about 1.05 times that of Earth and a mass roughly 0.93 times Earth's. These Earth-like dimensions suggest that TRAPPIST-1f could have a gravity and surface environment somewhat familiar to us, which is an encouraging sign for its potential habitability. One of the critical factors in determining the habitability of TRAPPIST-1f is its climate and atmospheric conditions. The planet's equilibrium temperature, which is the temperature without atmospheric effects, is estimated to be around -4 degrees Fahrenheit, or -20 degrees Celsius. This temperature is cold, but still within the range where liquid water could exist if the planet has a thick enough atmosphere to provide a greenhouse effect. The possibility of a substantial atmosphere on TRAPPIST-1F is crucial. If the planet has a dense atmosphere rich in greenhouse gases like carbon dioxide and methane, it could trap heat and raise the surface temperature to levels where liquid water could persist. The presence of an atmosphere would also help protect the planet from the star's radiation and maintain stable climate conditions. TRAPPIST-1F's potential to support water extends to the possibility of a global ocean. If the planet has a significant amount of water, it could create a stable and habitable environment. The idea of an ocean-covered world is intriguing because oceans play a crucial role in regulating climate and supporting life on Earth. Unlike its inner neighbors, TRAPPIST-1D and TRAPPIST-1E, TRAPPIST-1F is less likely to be tidally locked, meaning it could have a more even distribution of temperatures across its surface. If the planet rotates, it could avoid the extreme temperature differences between the day and night sides that tidally locked planets experience. This rotational movement would help create a more stable and habitable climate. However, TRAPPIST-1F's habitability is not without its challenges. The frequent stellar flares from TRAPPIST-1 could pose a threat to the planet's atmosphere and surface conditions. These flares release intense radiation that could strip away the atmosphere or harm potential life forms. A strong magnetic field, like Earth's, would be essential in protecting TRAPPIST-1F from these flares. Studying the TRAPPIST-1 system, with its fascinating array of Earth-sized planets, presents several unique challenges. TRAPPIST-1 is an M-type red dwarf, a category of stars known for their high activity levels. These stars emit powerful flares several times a day, which can drastically affect the planets orbiting them. Stellar flares release intense bursts of radiation, which can strip away planetary atmospheres, making it difficult for life to survive. This radiation also complicates the study of these planets, as the flares can interfere with the data collected by telescopes, making it challenging to discern between the star's activity and the planet's characteristics. Despite these challenges, scientists have developed advanced observational techniques to study the TRAPPIST-1 system. The James Webb Space Telescope, JWST, is a game-changer in this regard. With its sophisticated instruments, JWST can analyze the atmospheres of distant planets by observing the light that passes through them during transits. The Near-Infrared Spectrograph, NIR-SPEC, and the Mid-Infrared Instrument, MIRI, are particularly useful for this purpose. One technique used to study these planets is the transit method. When a planet passes in front of its star, it blocks a small portion of the star's light, causing a temporary dip in brightness. By carefully monitoring these dips, scientists can determine the planet's size, orbit, and sometimes even its atmospheric composition. The precision of the JWST allows for detailed analysis, even in the presence of stellar flares. By observing multiple transits, researchers can average the data to mitigate the effects of the flares and extract reliable information about the planets. Another technique is the radial velocity method, which measures the star's wobble caused by the gravitational pull of orbiting planets. This method helps determine the planets' masses and provides additional information about their orbits. Although TRAPPIST-1's stellar activity can complicate these measurements, combining data from different observational methods enhances the overall accuracy and reliability of the findings. Future missions are poised to further unravel the mysteries of the TRAPPIST-1 system. The European Space Agency's Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey mission, set to launch in 2029, will focus on studying the atmospheres of exoplanets, including those in the TRAPPIST-1 system. Ariel will complement the JWST's observations by providing a broader survey of exoplanet atmospheres, helping to build a comprehensive understanding of these distant worlds. Another upcoming mission is the Extremely Large Telescope, ELT, being constructed in Chile by the European Southern Observatory. Set to begin operations in the late 2020s, the ELT will have a 39-meter primary mirror, making it the largest optical telescope in the world. With its unprecedented resolution and sensitivity, the ELT will be able to directly image some of the TRAPPIST-1 planets, providing detailed views of their surfaces and atmospheres. In addition to these missions, Ongoing improvements in ground-based observatories and space telescopes will continue to enhance our ability to study the TRAPPIST-1 system. Advances in data processing and analysis techniques will also help scientists better interpret the complex signals received from these distant worlds. As we look into distant, possibly habitable worlds, we also find some planets that look like they come out of our worst nightmares. On the video appearing on your screen now, we talk in depth about the most horrifying planets ever discovered by humanity.